Welcome to Coffee and Conversation. My name is Honorine, and today I'm with Ryan Kim, who is a PhD candidate in physics at Florida State University. Welcome, Ryan, and thank you for being with me today.
Yeah, thank you for having me.
So my first question for you is, can you introduce yourself? Who is Ryan Kim?
My name is Ryan Kim. I finished my second year in the PhD program in physics here at Florida State University. So going into my third year. My research is in experimental high energy physics or particle physics. And what else is there? I'm originally from South Korea. I was born in South Korea and lived there 10 years. And then I moved to the United States, specifically Indiana, in 2007, so quite a long ago now. Did my undergrad at the University of Notre Dame in South Bend, and then I just came here to Florida State just a couple of years ago in the fall of 2019.
Nice. Did you move with your family, or did you move to study in the US and then you basically...
Yeah, we moved. My family moved. So my sister, my mom, my dad, we all moved to Indiana. My dad actually, we moved for me and my sister's education. So my dad actually oftentimes stayed in Korea to work while coming back and forth to visit. So a big sacrifice from my parents, for sure.
Yeah. Okay, so second year here at FSU, going on your third year, which means that you were a first year when COVID hit, right?
Yes, yeah, that's true. Yeah.
And you were not a freshman, but a first year PhD student at FSU coming from Notre Dame. How was it? How was it to be in a new environment, completely new environment, and moving online, moving everything online?
Yeah. Well, so when I first came, we were still, fall of 2019 before COVID. I had about 6 or 7 months before COVID hit. So it was really nice to, at least for my cohort, to be able to actually, meet people in person. I feel like I set a good foundation in those months. Of course, we didn't know COVID was coming, but I was able to meet a lot of new people and meet my cohort, meet the other people in my department. So that was, of course, it's a hard transition for anybody when moving to a completely new place and starting a grad program. The first semester was just really hard. A lot of, the coursework was really difficult. Teaching, like instructing labs on my own for the first time, which was difficult too. So it was a difficult semester, but I think it was really nice that, at least for my cohort, we got to meet each other so that when the pandemic hit and we moved online, we at least had some foundation to go off of, some relationships that we had formed, compared to, the cohort that came in 2020, which, I think they did a fantastic job getting to know each other online. But, I can only assume that it's different compared to having started in person. So yeah, the transition was definitely difficult going online, but, our classes moved online, our labs moved online, which is an interesting experience, teaching labs, using simulations, and then getting to do research online as well, which we can talk more about the research and how that was affected. But yeah, it was a difficult transition, but I think all things considered, it's been okay. Yeah, it was okay. I've been able to somehow, luckily, not get too far behind because of COVID and being online. So
let's talk more about your research. So you said your research is particle physics. I am in humanities, so I don't know much. So can you explain in simple terms what your research is about? Yes.
So, okay, well, almost everybody, you included, and everybody listening has taken, high school chemistry at least. And of course, you know about the different elements, right? So you got the hydrogen, helium, and all of those. And what separates these things is they're made up of atoms, right? There's the hydrogen atom, there's the helium atom. And what separates them is how many protons are inside the small nucleus of that atom. I haven't lost you yet, right?
A little bit, but I'm still following. I'm still there.
Okay. So basically, sorry, what I'm trying to get at is we, as a particle physicist, we study the smallest building blocks of matter. So what I'm trying to get at is, we break down things that we see around us at the very smallest possible scale. So we are made up of, like I said, hydrogen atoms, carbon atoms. Water molecules are hydrogen H2O, hydrogen atoms, and then oxygen atoms. When you break that down, when you break down an atom, you have a nucleus at the center of it, and you got electrons going around. And nuclei are made up of protons and neutrons.
Okay.
And then you can ask the question, what are protons and neutrons made of? And the answer is quarks and gluons. And then you can ask the question of what is a quark and gluon made of? And our current answer to that question is nothing else. A quark and a gluon is the smallest piece of matter that cannot be broken down into smaller pieces. And we call that particle a fundamental particle. Okay. Now, it's to be noted that the word atom, which the ancient Greeks came up with, I think you are in linguistics area a little bit, you might know that the word atom came from the Greek word atomos, which meant indivisible. They thought the atom was the smallest thing that cannot be broken down further. But in the many years of science since, we know that it can indeed be broken down further, and all the way down to the quarks and the gluons that I mentioned. But just as the ancient Greeks thought that their thing was indivisible, and we think that this thing is indivisible, it's totally possible in the future we find ways to break down quarks and gluons even further. We just might not have the right technology or equipment to kind of probe at smaller levels. But as of right now, we believe quarks, gluons, and actually the electron that orbits the nucleus, electron is not a quark or a gluon, but it is also a fundamental particle. So we have we have a set of fundamental particles, 6 types of quarks. There's 6 types of leptons, which includes the electron. You got other funny names like muons, taus, neutrinos. And then you got 5 types of bosons, which includes the gluon, the Higgs boson, the photon, the light particle, and then other things as well. So we have all these fundamental particles. They're all different, and we say there's 17 of them. And we organize them in a chart that we call the standard model of particle physics. So the standard model of particle physics is supposed to make up everything around us, including you and me and the stars. Because, again, the quarks and the gluons make up the protons and the neutrons. And then there's the electron, and then together they make the atom, which then combines to make elements, which makes up everything. Okay. So particle physics studies matter, things around us at the smallest scales, specifically the standard model of particle physics. The problem is, when we have the standard model of particle physics, even though it should explain everything, in fact, we look at the universe, and we have some overlapping with astrophysics as well. But you see things out there like dark matter and dark energy. You might have maybe heard of these terms. Yeah. But these are phenomena that exist in our universe that we know is out there, but it's not made up of these standard model particles. We cannot understand it via the standard model, which begs the question, hold up, we thought this was supposed to explain everything that we see, but there are things like dark matter and dark energy, which actually, crazy enough, makes up 95% of the universe's energy. So normal matter, like you and me and the stars, only actually make up 5% of the universe in terms of its energy, and that's what the standard model describes. So in fact, we do not understand 95% of the universe and what it's made of. So clearly, if the standard model was supposed to explain everything, it's not doing a good job. It's either wrong at some places, which we have a pretty good understanding of the standard model, but we're always trying to understand it better. Or more likely, there's new physics beyond the standard model that we just simply don't know yet. So this model that we have, even though it works pretty well, there's going to be new physics out there. So particle physicists are trying to probe at this new physics. And we do this in many different ways. But one of the ways that we do it is, actually, you're French, so you of course, of CERN, most likely. Right at the border of France and Switzerland, near Geneva, we have this huge particle physics research institute called CERN, and it hosts the world's largest particle accelerator called the Large Hadron Collider, which is underground, 100 meters, and then its circumference is 27 kilometers. So it's a huge ring right at the border of France and Switzerland. And what it does is it accelerates protons, which is the thing that makes up the nucleus, to nearly the speed of light, going in 2 different directions, and it collides these protons. And kind of what you can think of is, I said earlier, protons are made up of quarks and gluons. So when you collide these things at very, very fast and high energies, you can imagine like two Lego blocks being crushed at each other at very, very strong, very high speeds. You're going to see all the smaller Lego blocks kind of flying everywhere, right? And that's kind of what we see at these experiments. When they collide, we see quarks and gluons going everywhere. But also because of Einstein's famous E equals mc squared, which means energy is equal to mass times the speed of light squared, a lot of that energy gets turned into other mass as well. So even though the protons are not made up directly of electrons and other particles, you also see the energy gets converted into electrons and all of the other particles in the standard model via fancy quantum mechanics stuff that we won't get into. But basically what happens, you see a spray of fundamental particles from the standard model. So we study that. We have a huge particle detector in SPOT with very, very sophisticated technology in electronics. We take data on that moment, and then we're able to see exactly what happened in that moment of the collision. You can kind of tell what the different particles are. And we're also, like I said, we're looking for new physics. So we're looking for things that happen in our detector that we don't understand. So we actually don't like it when we see something we do understand, because we're looking for new things. So we're looking for things that we don't understand and looking for new types of particles that happen or that come up in that moment of the collision. And that's what I do. That's my research, is to look for new physics, new particles at the Large Hadron Collider.
Wow, this is fascinating. But it sounds like looking at this new physics, it sounds like a project that will never end. Or it sounds, to me, it sounds like a huge PhD project.
Yeah, so, well, I guess I didn't mention, the thing that I didn't mention is that the Large Hadron Collider is absolutely an international project.
Okay.
We have over 10,000 people from over 150 countries coming together to work at the Large Hadron Collider. Some of them directly there at Switzerland, but a lot of people working from their home institutions, like in my case currently with my advisor as well.
That's very fascinating. So at Notre Dame, you majored in physics and you minored in Italian, which is
yes, I did.
Opposite worlds. Very. So how did you get into Italian? Why did you decide to major in Italian? You also studied abroad in Italy.
Yes, yes.
So you're very interested about, fascinated about the deep meaning of the world and languages, which usually, I'm into language and I don't think about the world around me.
Well, I maybe, saying that I was very deeply interested is a little bit of an overstatement, because I mean, of course I am interested in it. I grew up in Korea. I already have a bilingual experience with Korean and English. So I was always interested in learning more about other cultures and languages. But the main reason I studied Italian was actually so that it helped with my physics. And let me explain that a little bit. So sophomore year of undergrad, I was trying to decide, most of the students go abroad in their third year. So I was trying to decide if I wanted to go study abroad. And I was a little bit hesitant at first, but then I found this program. Notre Dame has a very, it's a Catholic university, and Rome, of course, being where the Vatican is, has a lot of good connections with Rome. And they had many programs over in Rome. And one of them, this program called Rome International Scholars Program, really great program. It allowed the student to be in Rome, live with a host family, conduct the research of their choice, or whatever research project they wanted to do, like do an internship, and also take classes in Italy and learn Italian. And I was like, oh, if I wanted to do study abroad, I want to do something very immersive. But also, it was one of the only programs that would allow me to do research abroad. And I wanted to get my net wide, build more connections. So I started looking into this program. They hadn't had science students before. It was mostly for humanities students, but I managed to contact a professor in the physics department at Notre Dame who had collaborators in Rome, working exactly on the Large Hadron Collider, and specifically the compact muon solenoid experiments, which I had begun as an undergrad at Notre Dame. So I got connected with professors at the University of Rome Sapienza, doing work, the particle physics research. So I was able to get that set up, and I applied for this program, and I got in. So I started learning Italian basically in order to do this program, because you needed to have a couple semesters of Italian. So I learned it. I had taken some Spanish in high school, so it was easy to learn because there's a lot of similarities, but they were similar enough that I had to forget a lot of my Spanish, so that I can make way for the Italian to come in. But I was able to learn the language, and then I went over there. I had a fantastic time. I still think being at Rome was one of the highlights of life so far.
Yeah, I mean, my study abroad was also a highlight, even though I still feel like I'm studying abroad as an international student. But my
Yeah.
experience as an international, it's different to study abroad and to be an international student in the university.
Yes.
The expectations
Yes,
are different.
exactly. Yeah.
But so why Italian when you keep bringing up the CERN institute at the border of France and Switzerland, and I feel like French would have been maybe more helpful for you.
So you're right. So so FSU sends the grad students over to CERN, so I might be able to go sometime maybe next year. Not quite yet, but when you go, and I was able to go to CERN for a couple of weeks while I was in Italy. It's in Geneva. Everybody's talking in French, and even though the language at CERN, the official language that everybody uses is English, and everybody communicates in English. You step outside of CERN, and everybody's talking in French, and most people don't know how to speak English. And I remember being at a grocery store while I was there, and just not being able to communicate whatsoever with the French people. So sometimes I'm like, oh yeah, maybe French would have been helpful. But actually, besides, I think, or one of the largest demographics of people at CERN are Italians. So they and a lot of actually like higher up in administration also tend to be Italian people as well. So I think I didn't purposely choose Italy, but I think the fact that my professor, my undergrad advisor at Notre Dame, had a connection in Rome was not by coincidence, because there's just so many Italians working at CERN, and yeah. So I guess maybe French would have been helpful, but I am very glad. I mean, I really love the Italian culture too. Being able to, when I got there, to experience it, and the food is, I mean, so good. French food is good too. Don't get me wrong.
Oh no, I mean, I'm French. I love French food, but Italian, it's a different type of food. And yeah, well, thank you so much for your time. This was very interesting. I learned a lot about the atoms and all the molecules. So thank you for that. And I wish you good luck with the summer, with the research, and on your path.
Yeah, thanks so much for making the time to do this with me. That was a really enjoyable conversation. Thank you.
Thank you.